All right, so I think we'll get started here. So today, we'll finish chapter 9, and then we'll probably get started on chapter 10. Okay, so the goal is to finish the lecture by Monday on the last week of lab. So then on Wednesday, for Wednesday's lab attendees, you'll take your exam, final exam on Wednesday, and then Friday's group will take exam on Friday. Okay, because this final for this class is scheduled on Friday. We cannot take both sections on Friday, so we have to separate that way. Okay. All right. So homework 9 is up online. It's due next Tuesday. Okay. And then for this week's lab, we will be doing momentum and collision. So again, I will emphasize again, just bring your face shields in the lab. So whenever you guys are face to face, put your face shield on. Okay, so I don't want any like more people going into quarantine. All right. So and then the exam 3 arrangement will be like next Friday. The Friday lab attendees will take exam 3 on Friday, and then Wednesday group will take on the Monday after next week. Okay, so it's going to be on Monday. So today's class on disinfection, Jaden and Grant. Okay, you guys will take the responsibility. Okay, so only a few seats here in class. All right. So let's check what we learned last time. So last time we started chapter 9. Basically, we talk about the static equilibrium. So there are two conditions for an object to be in static equilibrium. The first is net force equal to 0. So that means if this is one dimension, then you have net force equal to 0 in one dimension. But if it's two dimension, then you'll expand it to the x and y direction. Okay, the two components to be 0 net force. And then for the second condition, we had to take a look on the new quantity called torque, which is the cost of the object that is rotating. If there's a force on the object over here, then it will make the object rotate with the x rotation. Okay, so then R times F times sine of theta, that is angle between this R and the F. Okay, so that gives you the magnitude of the torque. Okay, so RF sine theta. You can also do R sine or RF. Yeah, you can also do R sine theta F. So then R sine theta is the lever arm. Okay, so which is this from x rotation to the line where the force is acting at. Okay, on the object over here. So that's the lever arm. Okay. All right. So then for torque, it actually has also direction counterclockwise to be positive and then clockwise to be negative. Okay. So then the second condition that is necessary to achieve a static equilibrium is net torque should be equal to 0. Okay. So both conditions has to be satisfied. And then if the object is in static equilibrium, then you can actually pick your axis rotation as you like. Okay. The goal is to when you have the choice of your axis rotation, that will make the calculation the easiest. Okay. All right. And then if this is a two-dimensional problem, then you can write three equations. You can have net force in x direction equal to 0. You can have net force in y direction equal to 0, plus the net torque equal to 0. Okay. Then we took a look on the stability. So if an object is in equilibrium, then there's different scenarios. It could be unstable equilibrium. That means if it's moved from the original equilibrium side, you actually will return to the equilibrium side. Okay. And then there's second scenario, it will not return. So that's called unstable equilibrium. Okay. And then a third scenario called neutral equilibrium. So over here, then if you move to another position, you will stay over there. It's called neutral equilibrium. Okay. We also took a look on center of gravity or center of mass. So a system can be balanced at its center of mass. So then you can treat as all the gravity or the weight will be acting on that point for the system. Okay. And then if you have two objects in the system, the center of mass, if this is one dimensional, then the location for the center of mass can be determined by m1 times location of the first object plus m2 times x2, the location of the second object, and then divide by the sum of the two masses, or the capital M. Okay. If you have three, you can do similarly, just on the numerator plus m3 x3, and then in the denominator plus 3, or sum all the masses up in that way. You can expand this into two-dimensional, so then the center of mass will have an x coordinate and then a y coordinate. Okay. Similarly, for the y, you just replace x with y here to calculate this guy. Okay. And I believe you guys will get a problem in the homework assignment that is calculating the center of mass in two-dimensional. Okay, so basically you'll use these two equations. Okay. So the velocity for the system can actually be treated as the velocity at the center of mass. So in the similar fraction, it's going to be m1 v1 plus m2 v2 divided by the combined mass. Okay, if you have two objects in the system. Now keep in mind velocity is a vector. So then if this is two-dimensional, you'll have to do the components. Okay, so the x component, y component. All right. So today we will check on application of statics, including problem-solving strategy. So, so the first step is to determine if the object or the system is in static equilibrium. Okay, so that's the key here. And if it is, then you can apply net force equal to 0 and then net torque equal to 0. Okay. You will draw free body diagram of the system. That means you want to indicate all the external forces on the system first, okay? And then label them, and then possibly you'll resolve the forces into x and y components, okay? So, and then apply the net force equal to 0, net torque equal to 0, and then solve for the unknowns, okay? So we'll take a look one more example here for today. I think we had a look at couple examples last time, but one more here today, okay? So this one says, in this figure here, it's found out of the textbook. The CG means center of gravity or center of the mass. So it's located over here. All right. And then this pole is 5 kilograms for the mass. It's held by the pole vaulter at this two locations. Okay. So 2 meters away from the left hand and 0.7 meters away from the right hand. So right hand here, this is 0.7 meters. And then from here to the left hand, this is 2 meters. Okay. Calculate the force exerted by his right hand and left hand. Okay. So I think I can give you guys a couple minutes to work on this. So for the pole here, you probably can realize that it's in static equilibrium because it's not moving. It's balanced out by those three forces. Okay, the weight, force by the left hand, and force by the right hand. Okay, so then you can apply net force equal to 0, and then you can also apply net torque equal to 0. Okay, the choices of the x rotation could be arbitrary because it's in static equilibrium. Okay. think actually it says this is 2 meters from the center of the gravity to this end. Oh, actually, no, it's from the left hand. So this is 2 meters. This is 0.7. All right, so let's take a look here. Um, so there are 3 forces over here. So you can apply net force equal to 0. They are all in y direction, right? So then this is the positive force, the FL. These two are the negative, minus FR minus W. That should equal to 0. Okay, so this is net force equal to 0. Net torque equals also should equal to 0. Now you have to decide which would be your acceleration. Okay, so let's see. You can actually So it could be arbitrary. Okay, you can take either this one as your x rotation where the force by the left hand is exerted at, or you can take this one. Okay, so either way, now you probably don't want to take this weight to be where is your x rotation, because this is a known force. Okay, so the choice would be where there's an unknown force acting at. That could be one of your choices for the x rotation, because in that way, then the unknown force will contribute to the zero torque. Okay, then you can only have in the torque equation, then you'll be just having one unknown force with a known force, which will give you easy solution to solve for one of the unknown force. Okay, so let's take on this one, your x rotation. So this is your axis rotation. Okay, that's according to what you pick. Now, if this is your x rotation, then torque by three forces, by this force will be zero. Okay, by this force will make the object rotate counterclockwise, so positive. So positive of Fr times 0.70 meters, right? And then by this weight will be negative, so minus that weight, okay, times this is 2 meters away. Okay, that should go to 0. Now you know weight is equal to mg, right? So it tells you the mass of the pole is 5 kilograms. So then that gives you the weight. Okay, so that would be 49 newtons for the weight. So then this is 49. Now look at the second equation here. You can solve for your force by the right, this guy, right hand, right? So Fr times 0.7 meters should be equal to weight times 2, okay, because the one subtract the other goes to 0, so the two should equal to each other. So 49 newtons times 2 meters, okay, and you want to divide both sides by 0.7 meters to give you the force on of this guy. So Fr is going to be equal to, over here it's going to tell it's 140 newtons, okay. So that's your the force by the right hand there. Okay. Now you have the force by the right hand there. You can solve for, going back to the first equation. Okay. You can solve for your force by the left hand. So force by the left hand should be equal to force by the right hand plus the weight. Okay. From here, it's going to tell you that because FL minus those two is going to be 0. So then FL equals to the sum of those two, right? So this is going to be 49 newtons plus 140 newtons, okay? So 189 newtons on the force by the left hand, okay? You can actually choose this as your x rotation, then you will solve for this first, okay? It's going to be turn out to be the same, 189, okay? So either way, but you probably don't want to take that as your x rotation. Okay, you could do that. I mean, then for the torque equal to 0, then you have these two forces. Okay, then you have to be solving. You have to solve for the two equations with two unknowns, which is still doable. Okay, but just a little bit more tedious than of taking one of this as your x rotation. Okay, so I think that's it for this one. Let me know if you guys have questions. All right. So let me see. Let's go back here. All right. So the next section in this textbook talk about simple machines, right? Machines are helpful, okay? Because sometimes we are lazy, or maybe you can say we are actually smart to design machines, right? So laziness is not necessarily a bad thing, right? Because we are lazy, so we invent a lot of machines, equipments, okay? So um, So the most simple thing in this figure here, it's this like a nail, what do you call this? A nail puller over here. Okay. So then so if you want to pick up the nail over here, just directly apply force over there. It's probably hard to do, but if you have a nail puller, then you can actually apply smaller force over here, okay, to get that out. That's because we are applying torque over here. So this lever arm is further away from this point, the pivot point, which will be the X rotation, okay? Then this over here, this small level arm here for the nail, the force applied directly to the nail here. So then by applying small force over here, you get can pick the nail out, okay? So so then your input force could be small, your output force by using this simple machine is larger. So then the ratio between the output force and the input force is called your mechanical advantage. Okay, so mechanical advantage is defined as the output force divided by the input force. You can just use the abbreviation here. So AMA stands for mechanical advantage. Okay. And this is basically from by applying torque. Okay, so from the input, torque by the input force should be equal to torque by the output force. Okay, and because according to the definition and then this torque equation over here, you will realize that mechanical advantage then is also equal to the input lever arm divided by the output lever arm. Okay, so usually the input lever arm is larger, the output lever arm is smaller. Okay, all right, and like the barrel over here. Okay, so you can actually your input force could be small compared to the weight of the load over here, right? Because the load, the center of the gravity for the load here is closer to the X rotation over here, okay, or the pivot point over here, and then this lever arm for the input force is much larger than that. So Li is much larger than Loo, okay, and then also for a crank like this, it's the same mechanism here. You have larger lever arm for the input force and then smaller lever arm for the output force. Okay. Sometimes we also use pulleys. Okay, so if you have a combination of different pulleys, so for example over here, if you apply tension force T, then due to the factor that tension is the same throughout the rope over here, so then there will be one tension here, one tension here, right? So then 2T is equal to the weight, right? So that means T is equal to half of the weight, or your mechanical advantage would be the output force, which is the weight, divided by T, which is equal to half of the weight. So then mechanical advantage here is equal to 2, roughly, okay? We say roughly because in real scenario, there's probably like light friction forces between the rope and the pulleys, okay? I think we have saw that in the Atwood Machines lab. So there's more friction force there. Now you can apply multiple pulleys, for example, over here. So then this is T here. So then roughly your output force is equal to 3T. Okay. So then load is 3T. Your input force is just T. So then mechanical advantage over here is roughly 3. Okay. Similarly here, if you have a different combination here, you can realize that. So if you put your input as T, then there will be 4 T's here, all right, roughly, minus the 4T minus actually the friction and then the mass of the pulley, okay, the pulley is there. So then roughly this is equal to 4, all right. Okay, so let's take a look on one example on mechanical advantage here. So it says, suppose you need the to rise a 250 molar a distance of 6 centimeters above the ground to change a tire. If you had a 2 meters long lever, where would you place the fulcrum if your force was limited to 300 newtons? So your Fi is limited to 300 newtons. Where do you want to place your fulcrum or the pivot point? Okay. So let's say you have a lever arm, something like this. So you probably have your mower at one end, okay, somewhere at one end over here. Now the question is, where is your pivot point? Okay. The force you can apply, Fi is equal to 300 newtons. And then the mower here, it tells you the mass, so then the weight will be exerting on this end, okay? This is the weight equal to mg. You can calculate that 250 times 9.8 meters per second square, okay? The whole thing is 2 meters long. So then we are looking for this x, okay? If this is x, then this is 2 minus x, right? From the pivot point to the input force. So that's your Li. Li is 2 minus x. Your Lo, lever arm for the output, is x, okay? So you should have the two, the Fi, Li equals to Fo, Lo, right? Where Fo is equal to the mg, okay? All right. So let's take a look here. So sometimes when a program give you some information, some of the information actually you don't use that. Okay. So for example, here it says you want to raise the mower 6.00 centimeter above the ground. So that doesn't actually apply to any of equation over here. So this is just a kind of like confusing piece of information over there. What you really need is just the mg, the mass, and then the input force, and then the whole distance. Okay, so let's see here. Let me see. Stop sharing. So then we'll have a larger view over here on the screen. Okay. So Fi times Li is equal to Fo times Lo. Okay. So 300 newtons times Li will be 2 minus x, right? And then that equals to, so these two combine, multiply each other, 9.8 meters per second squared. This is in kilograms. Okay. This is the Fo times x. Okay. So then you want to distribute 300 into the parentheses, into the two terms in the parentheses. So 600 newtons times meter. This should be in the unit of meter. Okay, so let me just leave out the units because I know everything is in SI unit. Okay, so 600 minus 300x equals to, so this guy multiply that guy, that gives you 2450 times x. Okay. So then move this to the other side to isolate x. 600 equals to 2450x plus 300x. Okay, that would be 2750x. Okay, equals to 600. So then divide both sides by 2750 to solve for x. Okay, so in that case, this is equal to 0.218. That should be in meters because I have everything in SI unit. Okay, so roughly 0.218 meters away from the end. Okay, over there. So this is the first part. I'll call it part A. The second part is asking us what's the mechanical advantage of the leveler. Okay, so mechanical advantage of the leveler is defined as FO over FI. All right. So then it's going to be FO be this multiplied by that. So 2450 newtons. Okay, the weight divided by your 300 newtons of force. Okay, that will give you roughly 8.17. Mechanical advantage is ratio of two forces, so it doesn't have a unit. Okay. All right. All right. So if you guys are clear, the next section I'll just briefly mention it. So it talks about forces and torques in muscles and joints. Okay, so there's a few examples you can check. So basically, the system, for example, if I'm holding a physics textbook in your hand, if you have a hard copy, but so then this is the whole system will be in equilibrium, in static equilibrium. Okay, so you can see there's a weight of force here. There will be center of mass of your forearm, and then there will be two forces by the two muscles over here. Okay, so then this is the system in equilibrium. Okay, you can just put like a whatever, like a straight plank as a model of your forearm. Okay, so and apply forces over there. Okay, so they should add up to be 0 for the net force, and then also for the torque to be 0. Okay, so there's some examples in that section. You guys can check it out yourself. So That will be it for chapter 9. So I think we do have like about 20 minutes or so. We can take a look on the first couple, maybe couple sections on chapter 10. Okay. All right. So in chapter 10, it talks about rotational motion and angular momentum. Okay. So rotational motion, one of the, I think we have checked part of it regarding. So it's kind of like a regular circular motion, right? So rotational motion, or you can say circular motion. Circular motion is just in the two-dimensional plane, but rotational motion, you can say it's more like a 3D rotational, okay? So, um, so this skater here, actually, if you guys watch figure skating, actually, there's a lot of rotational motion involved, okay? So then there's a lot of knowledge you can explore over here on the motion of the skater, okay? And then also like tornado is a rotational motion, okay? We will take a quick review on a few quantities we learned earlier. So the first one, again, will be the angular velocity here, or angular acceleration. Actually, this is continuing from what we learned before. So then for angular acceleration, similar to linear motion, we define as the change in velocity divided by change in time t. So omega here is the angular velocity, okay? And then angular velocity is defined as change in angular displacement divided by delta t, okay? So this guy has SI unit of radians per second squared, okay? All right. Connection between linear and rotational quantities, I think we have checked this earlier from time to time, but for the linear speed or tangential speed, that's equal to r times angular speed, okay? And then for the acceleration, tangential acceleration is equal to r times alpha, okay? So again, it will be similar to the angular position and linear position. For angular position, theta, okay, if you do theta times r, then that gives you linear displacement of the arc length, okay? And because if an object is rotating, then it's having circular motion, so then there should be also a centripetal oscillation. All right, so centripetal oscillation we learned earlier is equal to r times omega square or equal to v square over r, okay? So either way, and it has a SI unit of meters per second square, okay? So then for the oscillation overall, for an object that is having a rotational motion, it has a oscillation in the tangential direction, also has oscillation in the centripetal oscillation, okay? In the case that if velocity of the speed is changing, okay? If the speed is not changing, then this tangential oscillation equal to 0, then you only have oscillation in the centripetal direction, okay? But many times this will be also changing, the V will be also changing, so then you have that component, okay? So if that's the case, then you will have angular acceleration alpha, that's not equal to 0. AT is not equal to 0, so alpha is not equal to 0, okay? Or on the other hand, if alpha is not equal to 0, then you have AT, okay? You have acceleration in tangential direction, all right? Kinematics of rotational motion. So this will be similar to the kinematics of the linear motion. You simply just change the linear quantities to angular quantities. So for example, the velocity, angular velocity then should be equal to initial angular velocity plus angular acceleration times time t, okay? Where in linear motion, we say final velocity is equal to initial velocity plus acceleration times t, right? You just change everything into um, angular quantities here, right? So then for equation of motions, you can do analogs to linear equations. So then you can write out the equation of motions for angular motions or rotational motions, okay? So angular displacement is equal to initial, or angular position is equal to initial position plus the average, which means 1/2 omega 0 plus alpha, assuming alpha is constant, okay? So this equation applies only when you assuming the alpha is constant, or this, also these equations, okay? And then final position equal to initial position plus initial angular velocity times t plus 1/2 angular acceleration times t squared. So basically, similar equations with different notations. Okay. All right. Let's take a look on one example here. So it says the angular speed of a propeller on a boat increases with constant acceleration from 11 to 39 radians per second in 3.0 revolutions. What's the angular acceleration of the propeller? All right. So this one, it says the constant acceleration and refers to the angular speed. So you will realize this is for angular speed, right? Because it's radian per second. And also it says here angular speed. So then this acceleration, constant acceleration, should refer to constant angular acceleration then. So it's asking us what's the angular acceleration. That means what's alpha? We are looking for alpha here. So omega final equals to omega initial plus alpha times t. Okay. Equation of motions. Theta equals theta 0 plus 1/2 omega 0 plus omega times t. All right. And then theta equals to theta 0 plus omega 0 times t plus 1/2 alpha t squared. Omega square equals to omega initial square plus twice alpha times theta minus theta 0. Okay, so these are equation of motions. And then we should also list the knowns we have here. So it says omega 0 is equal to 11 radians per second, right? Omega final is equal to 39 radians per second. And then it says in 3.0 revolutions. Okay, so that means the change in the angular position is 3 revolution, right? That's the unit for angular position. This is in revolutions, so that means you want to convert into radians. So multiply by 2 pi because one revolution, that's 2 pi radians. Okay, so then 6 pi in radians. So that's equal to 6 pi in radians. All right. So we are given those 3 quantities, and then we have equation of motions. We are pretty doing what we learned earlier, the same, okay, similar to what we learned earlier for the equation of motions there. So check the equations one by one and then see which one you need to solve for the alpha, okay? So we probably wouldn't use the first one because we are not given in time t, right? And then the same here because t is not known, and then the same here, t is not known, okay? So then you probably will turn to the last equation over here to solve for your alpha, all right? So we'll use the last equation here. We are looking for alpha, so then we'll move this guy to the other side of the equation. So omega squared minus omega 0 squared equals to 2 alpha theta minus theta 0, which is the delta theta. Okay, so this is the delta theta. So then you can divide both sides by twice of delta theta, okay? 2 delta theta, and then that will give you alpha. Okay, so basically alpha is equal to the left-hand side of the equation, okay? So then you'll do 39 radians per second. Now do not forget to square minus 11 square radians per second, okay? Should be radian per second. Divide by twice of 6 pi in radians, all right? That will give you your alpha. You plug in your numbers into your calculator. So it's going to be 37.14. That should be in radians per second square, okay? For the angular acceleration. All right. Okay. So if you guys don't have questions on that example, we'll actually take a look on a second example here. Go back. So this one says at 3 o'clock, the hour hand and the minute hand of a clock points in directions that are 90 degrees apart. What's the first time after 3 o'clock that the angle between the two hands has increased by or decreased by half to 45 degrees? Okay, so this is kind of similar or the analog to in linear motion. If you have one object moving with a certain speed, right, and then there's a second object behind it, so this is kind of chase problem, right? So one is chasing another. In this case, the hour arm is this little red needle here and moves slower than the minute arm that's behind it, right? So then originally they are separated by 90 degrees. What will be the first time they are separated by 45 degrees, okay? So let's take a look here. Go over here, stop sharing. All right, so initially the angular position of the two arms are 90 degrees, okay? So we can say the minute arm initial, okay? So I'm going to say theta sub m, that means minute arm, and then 0 means initial, minus theta for the hour arm initial, that is equal to 90 degrees, okay? So that's what we know, all right? And then initial position for the minute arm, if you look at the clock, okay, like this, if you take the horizontal line to be your reference line, then counterclockwise to be positive. So then the minute arm should be at 90 degree, right? That's positive direction. So that's 90 degree. Your hour arm initial should be at 0 degree because that's the reference line, okay? All right. And then we are looking for the final position of the two. So this guy minus this guy equals to 45 degree, okay? How much time that takes? T equals to what, okay? When that happens, what's T? Now, I think we also know two pieces of information, right? We would know how fast is the minute arm is moving. So the omega for m, okay? So for the minute arm, if it goes one full revolution, so then the time it takes is 60 minutes, right? So then omega of m, then that's equal to one revolution divided by 60 minutes, right? Now that's equal to one revolution is 360 degrees because we are given angles in degrees, so we can use degrees here. Divide by this is 3600 second, right? So 60 times 60 to be in second, okay? So then this is equal to 1 over 10. I'm going to just use fraction here in the units of degrees per second, okay? For my hour arm, its angular speed would be in one revolutions, it takes 12 hour, right? So 12h. So then you can write this. One revolution is 360 degrees divided by 12 times 3600 second because each hour there's 306 3600 seconds in it. Okay, so then this would be 1 over 120 degrees per second. Again, I will just leave the fraction here. Okay. So then my final position for the minute arm should be equal to its initial position plus omega m times t, right? All right. Now I should point out this because the two arms, they are going clockwise, right? So this is going clockwise. This guy is also going clockwise. So then the speed should be negative, okay? So if we stick to that clockwise, counterclockwise to be positive, so this is negative, the originally, okay? So those two are negative speed. So then this is equal to 90 degrees, okay, minus 1 over 10 degree per second times t, okay? For the hour arm, final position is similarly the initial position of it plus omega hour times t. Okay, so then that's equal to 0 degrees minus 1 over 120 degrees per second times t. Okay. So then over here, you can take this guy into this equation over here, and then also this guy over there. Okay. So we are going to return back to this equation and then replace those two terms with these two expression over here. So then 90 degree minus 1 over 10 times t. Okay, I'm going to leave out the units degrees per second. Okay, minus theta h, which would be like 0 minus 1 over 120 times t. Okay, that equals to 45 degrees. Okay, we are going to leave out the units. So I have degrees per second, so that means final t when you solve for it should be in seconds. Okay. All right. So then you have one equation here set up. You have just the unknown of t in it. Okay. You can solve for the unknown of t. Okay. So this is 0, so that goes away. Minus minus becomes positive. Okay. So it becomes positive because you're minus and minus. So 90 minus 1 over 10t plus 1 over 120t equals to 45, right? So you'll move this terms with t to one side of the equation, all right? Or isolate them, or whatever you want to say. But let me do 90 minus 45. So that means I move this guy over, this two to the other side equation. So this two to the other side equation, positive because it was negative, now it becomes positive, and then negative because it was positive. So 45 on this side, and then this is 1 over 10 minus 1 over 120 times t. Okay. Now you can put those numbers into a calculator. So basically 45 divided by 1 over 10 minus 1 over 120, okay, in parentheses, that will be your t. So t is equal to 45 divided by 1 over 10 minus 1 over 120. That's going to be 490.91 seconds, okay, which is roughly 8 minutes 11 seconds. Okay, so the next time when they make the 45 degrees, it's going to be at 3 o'clock 8 minutes and 11 seconds. Okay, in that sense. All right, questions you guys might have? All right, so then we'll just stop here for right now because we are running towards the end of the lecture time. Okay, so see you guys Friday in lecture.